Hey everyone, welcome to our first lesson in acids and bases. Let's go ahead and get our objective today is to compare and contrast properties of acids and bases and eventually salts. The note packet will be doing 2 to 4 and the homework will be vocab unless we want to add a little to that. So anyway, go ahead and open up your packet. We're working in the note packet today, a new note packet, acids and bases. Make sure you got the right one. It's right in the just flipping through here, you'll see it's right in the shelf if you didn't already grab it. These are some of the unit vocabulary we'll be learning today. These are the objectives, and we'll be working on comparing and contrasting acids and bases, like I said. So let's go ahead and dive in. We got Table K, which will be our area we can look up for common acids. You'll see all these common acids that we use, and I'll be talking about what acids are, how they are different than bases, and different than just other solutions specifically. So we already learned about solutions. The first thing I want you to see is we have some dilute acids. So we have some dilute acids. I need to zoom in a little bit here. So we have some dilute acids. Sorry about that. And they actually have like a sour taste, something that I don't want you guys to ever test yourself. It's just that's the nature of them. You might recognize it in the flavor of fruit flavoring. Citric acid is found in orange and lemons. Acetic acid is in vinegar. Carbonic acid is soda. And that's a little bit different than some. But boric acid, like eye washing, so you might use that for your contacts. Now, just because it's dilute doesn't mean it's a weak acid. So this is not the same as something we'll talk about later, which is a weak acid. This is not a weak acid. Sorry about the writing. Hopefully that improves. You can also have a concentrated acid. Now, this is the one you want to worry about. We already have actually worked with concentrated acids, actually to dissolve the penny. This thing burns skin, so that's why we're so careful with it. And it can eat holes right in clothing. I say eat, it's not very scientific, but it'll burn right through your clothing. They're always aqueous solutions. We mix them with water, and they all are electrolytes. So that means they allow the carrying of electrons or electricity, electrolytes. Now, the idea is that if you increase the concentration of the acid, you're going to get more ions. So concentration of the ions, oops, we just fixed that. More concentrations of ions mean it's more conductive. There's acids that are super strong, which means they dissociate in water very well, and they're called strong acids. It's not the same as dilute or concentrated. This is a strong acid. And strong acids are great conductors. They're very good conductors because they 100% dissociate. That's like dissolving in water. Dissociation means they take apart into its ions. So examples of those are HCl, which is the most common one we use in lab. Hydrobromic acid, so HBr. Hydrogen iodide, so iodoic acid, easiest to remember. And then sulfuric acid and nitric acid, HNO3, and hypochlorite, HClO3. Oh, sorry, HClO4. Okay, now there are weak acids, which means they simply don't dissociate as much. And they are poor conductors because there's not many ions in the solution. So that's basically all the other acids we come across. Okay, some things about acids. Well, you probably already know there's a thing that's the opposite of acids, and that's called a base. We'll talk more about those later, but acids react with bases. So if you ever have an acid spill, technically you could neutralize it with a base. and they form neutral solutions. So it's no longer acidic or basic once you combine them. It involves a double replacement reaction, which we've worked on all year. Double replacement reactions are when both partners exchange. So double replacement. The reaction type, like we learned about combustion, we learned about the Haber reaction last year. This one is double replacement reaction is called a neutralization reaction, specifically because it neutralizes a base or an acid. So the overall formula for it will follow like an acid. You have an acid, you combine it with a base. And the interesting thing is you always get the same two things out. You're always going to get salt, and you're going to actually produce water from the hydroxide in the hydronium ion. So you'll get salt and water back. So for example, we'll get a hydrogen, hydrochloric acid, and sodium hydroxide. And what will happen is the hydrogen from the hydrochloric acid will combine with the OH group, and the Cl and the Na will combine, the chlorine and the Na, to form NaCl. Oh, it's supposed to be NaCl. And then you'll also get H2O. I just want to emphasize where that's coming from. So you'll see the hydrogen. I do need another color, another highlighter. I'll have to find that later. I can't quite get it here, but we got the chlorine and the Na to form the sodium chloride. All right. Acids react with certain metals as well. And you might have seen that reaction when I had put magnesium in acid, and that produces hydrogen gas. If I don't do it or you don't remember, remind me when I come back and I will do that. This is a special type of single replacement reaction. And it can be found on table J. And table J is an interesting place because you can predict what will react. And we'll use that more later. The overall formula for this is you add an acid to a metal, and you'll always produce the same two things. It's sort of nice. You'll produce an anion, but you'll also produce hydrogen gas. For example, we have HCl, we have sodium metal. If you mix those two, you're going to get NaCl, and you'll get hydrogen gas. And this should be aqueous. Okay, what do acid and base reactions, what causes them? Well, or not what causes them. The reaction occurs because it's thermodynamically favored, but acids cause acid-base indicators to change color. So we can use indicators like litmus paper to change color. And that's going to be useful so we can know a solution is an acid or a base based on this. For example, litmus paper turns red when it encounters an acid. Oh, phenolphthalein does too. This is a tough one. So it's phenol, and then this is the hardest part, phthalate. Gosh, it's such a hard one to learn. Phenolphthalein, it turns from pink to colorless, for example. So you'll start off with something pink, and then you'll see it turn colorless in an acid. And litmus paper will just turn red. Acids have pH values, which we'll talk more about below. The pH value less than 7, so there'll be low numbers. And it's weird because you got really acidic, but that's a low number, so it'll be less than 7. And they fall on the lower end of the pH scale. Now the way the pH scale works is not as clear cut. It's not like it's acidic 0 to 14 scale. It's what it is It's a scale where 7 is neutral. You have an equal balance of hydrogen ions and hydroxide ions. But if you get more towards the acidic ions, you get a whole bunch more hydrogen ions. And over here, you're dominated by hydroxide ions, and those are called bases. So you have an acid on this side and a base on this side, and in the middle is neutral. Its general formula for acids is HA. So that just means hydrogen is usually found in acids, and we'll talk more about that. You can also say HX. That's a form of writing a generic acid. Just remember the X and the A in this case represents an anion, such as, I don't know, any negative particle, but let's say chlorine, -1. Now, we will talk about pH. When pH is equal to 7, I just want to clarify, it means the concentration of the hydrogen ions is equal to the concentration of the hydroxide ions. So that's what a pH, when a pH is 7, this is what it implies. All right. And I think that concludes the notes today. I know it's a short day of notes. Look on Google Classroom. I should have a vocab activity for you to learn some of the terms we'll be using in this unit. And that's all I got for you. We'll see you next time.